The National Electrical Code, or NEC, provides specific guidelines for electrical installations to ensure safety and proper functionality. In the situation presented, there are potential violations of the NEC concerning the derating of parallel feeder cables and the sizing of motor cables. Let's examine the issues in detail. Firstly, regarding the derating of parallel feeder cables, the NEC addresses this in Table 310.16, which outlines the ampacity of conductors. When conductors are installed in parallel within a single conduit, the current carrying capacity must be adjusted based on the number of current carrying conductors in the conduit. In the given scenario, there are 6 parallel 500 kcmil conductors within a single 4-inch conduit. According to NEC Table 310.16, with more than 3 current carrying conductors in a raceway or cable, a derating factor must be applied. For the specific case of 6 conductors, the derating factor is 0.8. This means that the ampacity of each conductor must be reduced to 80% of its original value. The calculation is as follows: the total feeder current is 800 amps, and this current is divided among the 6 parallel conductors. To determine the minimum ampacity required for each conductor, the following formula is used: required ampacity equals total current / derating factor x number of conductors. Plugging in the values, we get required ampacity equals 800 amps / 0.8x6, which equals 166.67 amps. Therefore, each of the 500 kcmil conductors must have an ampacity of at least 166.67 amps after derating. Now, let's consider the ampacity of 500 kcmil conductors. According to NEC Table 310.16, a 500 kcmil copper conductor with a temperature rating of 75 degrees Celsius is typically rated for 380 amps. However, this value must be adjusted for the derating factor. After applying the 0.8 derating factor, the adjusted ampacity becomes 380 amps x 0.8, which equals 304 amps. Since 304 amps is greater than the required 166.67 amps, the 500 kcmil conductors would appear to be adequately sized based on the initial calculation. However, there is an additional consideration, that is, the termination temperature ratings. The NEC requires that conductors be terminated at equipment that is rated for the conductor's temperature rating. If the terminations are the transformer, the motor control center, or the conductors themselves are only rated for 75 degrees Celsius, then the 75 degrees Celsius column of NEC Table 310.16 must be used. If the terminations are rated for 90 degrees Celsius, then the 90 degrees Celsius column can be used, provided that the equipment is also rated for 90 degrees Celsius. Assuming the terminations are only rated for 75 degrees Celsius, the ampacity of a 500 kcmil copper conductor is 380 amps. After applying the 0.8 derating factor, the ampacity is reduced to 304 amps. If the total load in the feeder is 800 amps, each conductor must be sized to carry at least 800 amps / 6x 0.8 equals 166.67 amps. Therefore, a 500 kcmil conductors are adequately sized, even with the derating factor applied, if and only if you can use the 75 degree rating of 380 amps. If the terminations are rated for only 60 degrees Celsius, the ampacity of the 500 kcmil copper conductor is only 320 amps. After applying the derating factor, the ampacity is reduced to 256 amps. If the total load in the feeder is 800 amps, each conductor must be sized to carry at least 800 amps / 6x 0.8 equals 166.67 amps. Therefore, the 500 kcmil conductors are still adequately sized, even with the derating factor applied, and even with the 60 degree rating of only 320 amps. Secondly, considering the motor cable sizing, NEC Section 430.22 outlines the requirements for motor circuit conductors. This section mandates that motor branch circuit conductors must have an ampacity of not less than 125% of the motor's full load current, or FLC. In this case, The motors are rated at 150 horsepower, 460 volts, and have a full load current of 168 amps. Therefore, the minimum required ampacity for the motor branch circuit conductors is 168 amps x 1.25, which equals 210 amps. Furthermore, the NEC requires conductors and conduits to be derated based on a number of current-carrying conductors. In this installation, there are 3 size 1/0 conductors in a 1 and 1/2 inch conduit. Assuming these are the only conductors in the conduit, a derating factor may still need to be applied, depending on the specific conditions. The NEC states that if the conductors are installed in an environment with an ambient temperature higher than 30 degrees Celsius, 86 degrees Fahrenheit, an additional temperature correction factor must be applied, per NEC Table 310.16. Let's assume that the ambient temperature is within the allowable range and no temperature correction is needed. However, if the conductors are subject to heating from other sources, or if there are other conductors in the same conduit, a derating factor might still be required. For the sake of this example, we will assume that no additional derating is required beyond the initial 125% factor. The provided information indicates that size 1/0 conductors are used for the motor branch circuits. According to NEC Table 310.16, a 1/0 copper conductor with a temperature rating of 75 degrees Celsius is typically rated for 150 amps. Now, let's compare this to the required ampacity of 210 amps. Since the 1/0 conductors are rated for only 150 amps, which is significantly less than the required 210 amps, the motor cables are undersized and do not meet the NEC requirements. Let's review the ground conductor sizing. The equipment grounding conductor, or EG, must be sized according to NEC Table 250.122, based on the size of the overcurrent protective device. The overcurrent protective device for the motor branch circuit is typically sized at 250% of the motor's full load current. In this case, the motor's full load current is 168 amps, so the overcurrent protective device is sized at 168 amps x 2.5, which equals 420 amps. According to NEC Table 250.122, for an overcurrent protective device rated at 400 amps, the minimum size of the copper equipment grounding conductor is size 3. Therefore, the size 4 ground conductor provided for the motor circuits is undersized. In summary, there are 2 main issues with this installation that do not meet the NEC requirements. Firstly, the motor cables are undersized, as the 1/0 conductors do not have sufficient ampacity to carry 125% of the motor's full load current, and secondly, the equipment grounding conductor is undersized, as the size 4 conductor does not meet the minimum requirements outlined in NEC Table 250.122. In conclusion, the installation does not meet the NEC requirements for derating parallel cables and motor cable sizing, based on the information provided. It is important to consult the latest edition of the NEC and local codes for specific requirements and to ensure that all electrical installations are safe and compliant. Remember that this analysis is based on the information provided and certain assumptions. A thorough on-site inspection by a qualified electrician is recommended to verify the actual conditions and ensure compliance with all applicable codes and regulations. It is important to consult the latest edition of the NEC and local codes for specific requirements and to ensure that all electrical installations are safe and compliant. To elaborate, let's delve deeper into the specific NEC sections and calculations that support this conclusion. Firstly, examining the paralleled feeder cables. NEC Section 310.16, titled Ampacity of Conductors, provides the foundation for determining the allowable ampacity of conductors based on their size, insulation type, and installation conditions. This section references tables that list the ampacities of various conductors in different environments. As previously mentioned, NEC Table 310.16 is crucial for determining the ampacity of conductors based on insulation type and temperature rating. This table lists ampacities for conductors rated at 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. The appropriate temperature rating must be selected based on the terminations and equipment being used. Additionally, NEC Section 310.15, titled Ampacity Adjustment Factors, outlines the requirements for derating conductors when multiple current-carrying conductors are installed in a raceway or cable. This section directs users to Table 310.15 current, which provides adjustment factors based on the number of current-carrying conductors. As we discussed earlier, for 6 current-carrying conductors, the derating factor is 0.8. Applying this derating factor to the ampacity of the 500 kcmil conductors is essential to ensure that they are not overloaded. Secondly, focusing on the motor cable sizing, NEC Section 430.22, titled Motor Circuit Conductors, provides specific requirements for the sizing of conductors supplying motors. This section mandates that the motor branch circuit conductors must have an ampacity of not less than 125% of the motor's full load current, as determined by NEC Tables 430.247, 430.248, 430.249, and 430.250. These tables list the full load currents for various motors based on horsepower, voltage, and phase. In this case, the motors are rated at 150 horsepower, 460 volts, and are 3-phase. Consulting the appropriate table, we find that the full load current for each motor is 168 amps. Applying the 125% factor, we get a minimum required ampacity of 210 amps for the motor branch circuit conductors. Furthermore, NEC Section 430.52, titled Motor Branch Circuit Short Circuit and Ground Fault Protection, outlines the requirements for the overcurrent protection of motor circuits. This section specifies that the motor branch circuit overcurrent device must be sized according to the type of motor and the type of overcurrent device used. As previously mentioned, the overcurrent protective device is typically sized at 250% of the motor's full load current. This overcurrent device protects the motor and the branch circuit conductors from short circuits and ground faults. Regarding the equipment grounding conductor sizing, NEC Section 250.122, titled Size of Equipment Grounding Conductors, provides the requirements for sizing the equipment grounding conductor, or EG. This section directs users to Table 250.122, which lists the minimum size of the EGC based on the rating of the overcurrent protective device. As we determined earlier, the overcurrent protective device for the motor branch circuit is sized at 420 amps. According to NEC Table 250.122, for an overcurrent protective device rated at 400 amps, the minimum size of the copper equipment grounding conductor is size 3. Therefore, the size 4-gram conductor provided for the motor circuits is undersized. It is important to note that these calculations and conclusions are based on the information provided and certain assumptions. A thorough on-site inspection by a qualified electrician is recommended to verify the actual conditions and ensure compliance with all applicable codes and regulations. This inspection should include verifying the conductor types, sizes, and insulation ratings, as well as the ambient temperature and other environmental factors that may affect conductor ampacity. Additionally, the inspection should verify the ratings of the terminations and equipment to ensure that they are compatible with the conductors being used. Furthermore, the inspection should verify the proper installation and support of the conductors and raceways, as well as the proper grounding and bonding of all equipment. In addition to the specific NEC sections mentioned above, there are several other sections that may be relevant to this installation. These include NEC Section 300.11, titled Securing and Supporting, which outlines the requirements for securing and supporting conductors and raceways. This section ensures that conductors and raceways are properly supported to prevent damage and maintain their integrity. Also, NEC Section 300.14, titled Length of Free Conductors at Outlets, Junctions, and Switch Points, specifies the minimum length of free conductors required at outlets, junctions, and switch points. This section ensures that there is sufficient conductor length for making connections and performing maintenance. Furthermore, in NEC Section 314.16, titled Number of Conductors in Outlet Device and Junction Boxes and Conduit Bodies, outlines the requirements for the number of conductors allowed in outlet device and junction boxes and conduit bodies. This section ensures that the boxes and conduit bodies are not overfilled with conductors, which can lead to overheating and damage. In addition, NEC Section 314.17, titled Entering Raceways or Cables, specifies the requirements for the methods of entering raceways or cables into boxes and conduit bodies. This section ensures that the raceways and cables are properly secured and protected from damage. Moreover, NEC Section 350, titled Liquid-Tight Flexible Metal Conduit LFMC, provides requirements for the use of liquid-tight flexible metal conduit, or LFMC. This type of conduit is often used in industrial applications where flexibility and protection from liquids are required. It is important to ensure that the LFMC is properly installed and supported, and that the fittings are properly tightened to maintain a liquid-tight seal. NEC Section 250 provides comprehensive requirements for grounding and bonding electrical systems. Grounding ensures a low impedance path for fault currents, protecting equipment and personnel. Bonding connects non-current carrying metal parts to create an electrically conductive path, minimizing voltage differences and preventing shock hazards. Proper grounding and bonding are crucial for safety and code compliance. Moreover, NEC Article 100 defines essential terms used throughout the code. Understanding these definitions is vital for correct interpretation and application of NEC requirements. Key definitions include ampacity, conductor, equipment grounding conductor, bonding, and overcurrent protective device. A thorough understanding of these terms is essential for navigating the NEC and ensuring compliance. In conclusion, the electrical installation at the mining facility requires careful review and correction to comply with the NEC. Addressing the undersized motor cables, inadequate equipment grounding conductor, and proper derating of paralleled conductors is essential for safety and operational reliability. Consulting with a qualified electrician and adhering to the latest edition of the NEC are crucial steps to rectify these issues and ensure a safe and compliant electrical system. Remember that electrical codes and regulations are constantly evolving, so staying updated on the latest requirements is essential for all electrical professionals.